once a problem is formulated, solving it means finding an action sequence that reaches the goal or the goal node. To do this, we use search algorithms, which explore possible sequences in a search tree. The root is the initial state, like in Arad, and each branch represents an action, and each node is a resulting state. Like in this picture, Arad is the root or the starting state or the initial state, and then each branch represents an action, like traveling from Arad to Sibiu. And then each node is a resulting state. That means as a result of this action, we reach to the resulting state, which is Sibiu. We expand nodes by applying all legal action, generating new child state. Like from Arad, the legal actions are traveling to Zerinth, to Sibiu, and to Timisoara. The set of nodes waiting for expansion is called the frontier. Like for Arad, the frontier will be Zerinth, Sibiu, and Timisoara. This is kind of an open list. The search continues until we reach a goal or the frontier is empty. Frontier will be empty when there will be no more nodes to expand. So two issues can arise. One is repeated states. We can see here the tree search algorithm, which says that until there are no candidates for expansion, you kind of keep expanding. So repeated states can happen, like you have Arad to Sibiu, and then again Sibiu is when expanded, Arad will be counted as a child node of Sibiu. So Arad, Sibiu, in this way, it will create infinite trees. Also, there will be redundant paths, like multiple ways to the same state, like Arad to Sibiu is 140 kilometer or mile versus Arad to Zerinth to Oradia and to Sibiu is 297 kilometer. These two are different paths but redundant. To avoid waste, we use graph search instead of tree search. So these are the way tree search expands the tree, and we can see that Arad, Timisoara again to Arad. So this is creating the repeated states and redundant paths. So here, this is a tree. After the tree search, if it doesn't work, this is the implementation of the general tree search algorithm. But to avoid the tree search issues, we can use a graph search algorithm. So graph search adds explode set or closed list to remember the visited states. So when I'm traveling from Arad to Zerinth, the Zerinth will not, when Zerinth is expanded, it will not count Arad as its child node or its frontier because it already knows Arad has been visited. So we create a closed list to remember the visited states. That way we don't revisit or re-add the same state. Graph search ensures that the algorithm systematically explores the state space, separating explored and unexplored regions until it finds a solution efficiently. So graph search in this way is better than tree search, which will create repeated states. Now the infrastructure for search algorithms, how to implement search, we need some bookkeeping. Okay, each node in the state, keeps track of the state, the parent node, the action, and the path cost. So this will be here. The initial state, the successor function. After applying the successor function, I'll get all the children or the frontier. The goal test will check if the goal has been reached or not, and the path cost. Okay, so we have already discussed that. So now we are telling, it's important to note that a state is a configuration of the world, but a node is a record of how we reach that state. So the same state may appear in different nodes if we reach through different paths. This is important to note. So the next, we need a way to manage the nodes waiting for expansion, like the frontier. Okay, like for Ara, the frontier is Zerinth, Sibiu, and Timisoara. How we expand them. So there are multiple ways to maintain them as a data structure. Okay, so this is handled with queues, different types of queues. and that will kind of determine the search strategy. So one is the FIFO queue, which is the first in, first out, like a line in a cafeteria. You know, if you stand in the line of a Starbucks, if you are first in the line, you'll get the coffee and then you will leave, and the next person in the line will get it. It's called first in, first out. And it is used in a particular type of search. We'll talk about it, which is breadth first search. And then there is another type of queue, is a LIFO queue, or last in first out, LIFO or LIFO, L-I-F-O queue, which is basically is called a stack. So like a pile of plates. Again, in restaurant, somebody's cleaning the plate and piling them up. So there might be 20 plates, but when we pick them up, we pick it from the top, not from the end or the bottom. The end is here, actually the top. So it's expand like a pile of plates, and this kind of data structure is used in depth first search. There is another type of data structure, which is priority queue. It expands a node with the best score, any kind of best score. We'll talk more about it, like lowest score, lowest cost, or some kind of heuristic. Finally, to avoid repeated work, we maintain an explode set. Like we said, the graph search algorithm will maintain a set of explode or visited node. So here we maintain an explode set, which is a record of visited states, often implemented as a hash table for fast lookups. You can quickly check whether it's there already or not, visited already or not. To ensure correctness, states should be stored in a canonical form. So logically identical states map to the same entry. This is also important. This infrastructure, nodes, queues, and explode sets, forms the backbone of all search algorithm. Okay, so infrastructure you can call, data structure you can call, is basically the nodes, how you define the nodes, how you what kind of queue you uses, like a FIFO queue, LIFO queue, or priority queue, and the explode set of nodes. These three things are the backbone of all search algorithms we'll discuss. Now another thing we need to talk is the measuring problem solving performance. Okay, so we will discuss that in the next video.